All right, so part two of chapter 12, which is the third and final part of the nervous system. We started with the general senses and some of the special senses, and now we're going to move in and get to most of the rest of them, but they do take a little time. All right, so taste. Again, taste, it just like olfactory, is going to be one of those things that is a chemoreceptor. So it responds to chemicals that are entering into that space, so the oral cavity in there. So this is taste. Things you need to start getting used to terms and things. I mean, not that you haven't, but that respond to taste also. So what we have then is you have the tongue, and everybody thinks about the taste buds being on the tongue, but you do have them throughout different parts of the mouth also in there. So the roof of the mouth, linings of the cheeks and stuff in there. And as far down as part of the pharynx back in the deeper portion. Now, what you think of as being your taste bud is not actually your taste bud. So all those little bumps that are on your tongue. So you have these different types of bumps and stuff. Those aren't actually the taste buds themselves. Those are just areas, and then you get down to like the microscopic area, and the taste buds are in these small little cellular areas. We do have specialized taste receptors. Like I said, those are chemoreceptors. So the food or the water or the drink or whatever that's entering your mouth has specific chemicals in it, and those are going to stimulate those chemoreceptors. They're going to bind to those chemoreceptors and stimulate those. We have cells that contain those specialized receptors on there. So modified just epithelial cells that contain those actual receptors. On those receptors, we again have hairs, and you've seen it on several of these specialized cells where you have a cell and then it has the little hairs on the end. So those taste hairs or gustatory hairs are going to be the things that actually pick up on those chemicals, okay, protrude from them. So when we're looking at it, so here's what we tend to think of as being a taste bud is this whole protrusion that you feel on your tongue, but that is actually what we call a papilla. So papilla, we've seen lots of papilla come up lots of times, but each one of those is a papilla, and each one of those has these little grooves. So the chemicals come in, they wash across your tongue, your mouth, whatever, and they actually the chemicals then go into the grooves, and lining the grooves you have many, many little taste buds. So all these little dark spots that you see right here are actually the taste buds. So they're located within that. It's not the whole thing itself. That's just one papilla, and it contains many taste buds. So if I take one of those taste buds and I blow that up, you're going to see that there's a lot of cells. So you have a bunch of support cells, and then you have the actual taste cells. So I can see pink and yellow in here. The support cells are these pink ones, the epithelial cells around it. So all of these things are kind of supporting. The guys doing the work that are picking up on this are what's in yellow in this picture here. And they have little hairs. And see how you have, so I've got taste, chemicals that flow in here, chemicals that flow in the groove, and then the chemicals are going to have to flow into that little pore right there and come in contact with the ends of those little taste cells where you have the taste hairs located. And those are going to bind those chemicals and then set off a chain of reactions that sends that impulse along those nerves. We have, it says 5 primary taste sensations. Your book probably still says 4. It just depends on the source that you're going for. We grew up knowing about the 4, so sweet, sour, salty, and bitter. But umami is one of those that, it's been discovered. I mean, it's been about 100 years. I mean, we've known about it for a really long time. It's just that, things are slow, I guess. And some people don't really still put it in the textbooks as being a taste, but it should be. It's a 5th. It is that savory taste. So sweet is stimulated by carbohydrates, so sugars and fruits and those kinds of things. Little carbohydrates go into the sweet, even like sweet potatoes, vegetables, and things. Sour is stimulated by acids, and you get that extreme sour taste. And depending on your genetics, you may or may not like those as well. So it's just everybody has a little bit different genetics, learning, that kind of stuff. Salty is obviously with salt, and then bitter. You have all kinds of organic compounds that do the bitter, but you end up with that bitter taste. But umami is that savory taste. Now, along with that, there's other candidates that people think should be listed with the taste sensations. Dogs can taste water, and other animals too, but they know for certain with dogs. Water is vital to life, and it contains, we think of it as having no taste, but it really does have distinct taste, and you can definitely taste water from different areas, like hard water versus soft water in different parts, like whether that's nice tasting or not. Bottled water has a lot of minerals that have been taken out and then some added back in. What we taste in water really are the minerals and things that are in there. And so you're kind of picking up. So some people are like, water should have its own category, but maybe it's just stimulating some of these other categories in here. But there are specific taste buds for dogs. And think about how important water is. Well, I mean, we have to have water. So possibility that we have taste buds that we just haven't really nailed down that are stimulated strictly by water. Now, spicy is a different thing. If you have spicy foods and you like spicy foods, that has nothing to do with taste. So it's really, I mean, although the food itself is going to be stimulating one of these other five in here, depending on what food we're eating, the spicy part itself is really just pain. And what happens when you get pain is you send an impulse to your brain that says, wow, that was really hot, but oh, I like it. Because as soon as you get that, remember, we have our own internal little opiates that we release, our little endorphins. You send out some of those endorphins, and the endorphins say, that makes me happy. It's your own little happy drugs. And when you release those, the pain might be there, but the happiness is there too. So you're like, let me go for another bite. Let me scoop the tortilla chip into some more salsa or whatever it is, because of that reaction in the brain of releasing those little endogenous drugs that you have in there, the endorphins and stuff. Why would we do that? Why would we want to subject ourselves to pain? Normally, pain is something that says, don't go there, right? You're doing damage. But in this case, a lot of the spice that comes from food comes from peppers, right? So various different peppers that we have in there. And peppers are really high in vitamin C and vitamins A in some case. A lot of it's vitamin C, but a lot of different vitamins. And vitamins are nutritious. We need them. They're not going to give you energy or anything, but they're definitely needed in terms of your chemical reactions and everything that's going in the body. It's going to allow for all of your respiratory enzymes to work, and different other types of enzymes. Remember, we talked about that with coenzymes. So these peppers then are nutritious, and they also have carbohydrates in them too. But they're going to be things that we really, really would be a benefit to us. So for that kind of action in somebody who likes spicy foods, they're actually would be healthier than their counterparts who don't have that. So there's an evolutionary advantage to actually eating spicy foods. My mother-in-law thinks just black pepper is spicy, but each of us grows up, and a lot of that, some of that's learned, some of that's genetics in there. All right, so what happens when we get any one of those tastes actually that is being stimulated and then sent to the brain? So we have to send the taste receptors, go directly to some cranial nerves. Cranial nerves send it to the first step of the brain, which is the medulla oblongata, that sends it to the thalamus. Thalamus says, I'm aware of this. We reroute and we go to the sections of the brain that are going to interpret taste. Gustatory refers to taste. So gustatory cortex, the part of the brain that is interpreting this, is what we call the gustatory cortex. Smell and taste are both linked together a lot. So, like when you were a kid and you didn't like something and you said, hold your nose and you won't taste it, and that was a lie, but you still blunted your taste a little bit. You can get kids to eat a few things that way that they might not normally eat. It's because they're both chemoreceptors. So, you know, that you're getting that chemical reaction both ways from there. But also, we can have disorders that affect those tastes or even affect the smell. So, we can have lost smell, we can have lost taste when you have things like a cold or a flu. And remember, that's very much in the sinus cavity in there. So, if I have a cold or the flu that's affecting the cells in the sinus cavity, I'm not going to get that information, that those chemicals up to that olfactory, or those olfactory cells in the cribriform plate. So I may not be able to smell as well. Allergies also inflame the tissues in the sinus cavity, so you're going to have problems in there. You can have growths like polyps in the nasal cavity that are going to prohibit the ability of the chemicals to get to those cells. Swollen mucous membranes, again, that goes all back to being sick, right? Head injury. So if I injure the gustatory or the olfactory complexes that in the cortex that should be interpreting these things, a head injury could keep me from being able to interpret it. So everything might be working just fine all through smell and taste, but once I get it to the brain, you know, it's a dead end up there. Chemicals will actually burn the nerve ending. So a chemical exposure would burn those off. Sometimes that can be, you know, you'll get them back after a period of time. Sometimes, depending on the amount of damage that and the amount of exposure over a period of time, that may never happen again. And then nutrition plays into everything. So nutritional and metabolic problems or disease can also affect those receptors, and then you would have no sense of smell or an altered sense of smell. We can have temporary types of altered sense of smell. Taking drugs, whether prescribed or not, can also have an effect. So there are certain things that have sulfur in them, and sulfur has a very distinct smell. So a sulfur-containing drug is going to alter you're going to get that sulfur smell, and that's going to alter everything else that comes in because you're being overwhelmed by that sulfur sort of initiation of that chemical. Whether, you know, I'm taking the drug, I'm not really smelling that drug, it may not have a smell, but it still has the chemical. And if that chemical binds to those olfactory nerve endings or even the gustatory, you're going to get that weird taste and that weird smell that goes along with it. Tetracycline, which is an antibiotic, gives you a metallic taste. Chemotherapy is going to damage any cell that is actively going through mitosis. That's why it works so well on cancers, because it targets cells that are highly mitotic, and it can also damage the cells that are the receptors for taste and for smell too. So chemotherapy gives you this altered smell, and it really does work on the taste too. So you see a lot of chemotherapy patients who are like, they'll order something that sounds good or eat, you know, fixed food that sounds good, and once they take a bite or two, it doesn't have the flavor that they want, it doesn't have the taste that they want, and it makes it really hard for them to maintain adequate nutrition because they just can't eat at that point. But it goes through that. Paint strippers are chemicals. So paint strippers are one of those things that are very dangerous and can go in there and just damage, goes back to chemical exposure up here, damage that sense of smell and that sense of taste. Gives you a not very pleasant type of sense with that decay. All right, hearing. Hearing is a pretty complicated organ in there. We have to take in the sound waves in through our ears. We have to direct it to our ears. It has to go down that ear canal, and it has to go through a series of steps of transmitting that vibration, that first a sound wave to a mechanical vibration, and then to the receptor cells that are really deep into the skull, relatively speaking. So it does take a while to get to that point. Every single portion of the ear has to be able to effectively transmit that sound in order for you to hear properly. We have three sections of the ears. The external ear is what we can see. So that's the auricle, the ear that we see going into where you have the eardrum, the tympanic membrane, and then the middle ear, and then the inner ear. So we're going to talk about all of the different structures that are in each of those. External first, like I said, this is your ear that we see. We call that the auricle, so that's the term I want you to use. The job of it and the shape of it is to take sound waves that are coming in and direct them to that cavity, that canal, so that you can get the sound waves moving down the canal. Now, as humans, our ears are pretty flat against our skull and are fairly useless in that effect. So we don't have ears that really scoop up sound, but animals with, like ears on their head and they can move them can actually turn the ear to scoop that sound and pull that sound and direct it in. Ours are pretty flat, but it works. So that's all we really need. So we don't need to be able to move our ears and have those scooped ears, because we're not generally being either the predator where we have to find our prey and listen for every little movement of it. And we have the ability to, as predators, we have a lot of other senses we can use for that, even with hunters and things. But as prey, we're generally not the prey where we have to, life or death, something's coming up behind you. You need to figure out where it is and be able to listen as I'm feeding on the ground or something. So ours works good enough. This canal that then directs those sound waves in, so the sound waves are moving down the canal, that is called our external auditory meatus. That is something that you learn. So here's the skull, right? This is what we learn when we learn the skull. So it's partially the skull and partially this tissue, and you can see the yellow, the fat, and everything. So it becomes that elongated tube right there. The external ear ends when you hit what is shown here as the eardrum, but is what we want to refer to as the tympanic membrane. And that signifies the start to the middle ear. So here's the external ear. Again, auricle, sound waves come in. As soon as they hit the tympanic membrane, that is the end of the external ear. So external ear is from this point to this point, right in here. But the whole point is to capture the sound waves and move them in so that we can then start processing them. The tympanic membrane is commonly called the eardrum, right? And we know that from, it has to vibrate, and ear infections in children and stuff like that. The tympanic membrane has pressure. And it is like a membrane of tissue that has this shape to it. But its job is to pick up the sound waves. So I've got sound waves moving in this way. This is the first point that takes those sound waves and makes them physical. So they become a vibration. So this is a physical vibration, and then they're going to vibrate against everything in what is now going to become the middle ear. So the tympanic membrane is the end of the external ear, the beginning of the middle ear. Okay. Again, we've gone from a sound wave to now a physical vibration. So here's our eardrum right here. We have 3 bones that are the smallest bones in your body. These are called the auditory ossicles, and I'll come back to those. But auditory ossicles, ossicle refers to bone. They are taking that physical vibration that has now been the job of the tympanic membrane, take a sound wave and make it into a physical vibration. They're going to transmit that physical vibration all the way to this snail shell looking thing called the cochlea. But the middle ear is from that point here, so the tympanic membrane, to this point right here where that last little ossicle, I was drawing in here, that little U-shaped one right here, meets up with the cochlea. So at that point, that's the end of the middle ear. So all of this that you see right here is internal ear. So it's this cavity in here. Okay, so what we call the tympanic cavity. It is air spaced, should be. This is where you find ear infections. Since you have an external ear that is continuous with the outside environment, and then you have this air-filled cavity right here, that can become a problem. So if this area gets fluid in it, so it starts collecting some fluid in it, that can cause an infection. And what it's going to do is it's going to start filling up. And when it fills up with the fluid and it fills up with the infection, it's got to go somewhere. And this is all bone right here. There's nowhere to go to put pressure except to put the pressure back on that tympanic membrane. And what you'll see is that tissue gets pushed out backwards this way towards the external. The skin tissue, the epithelial tissue around it gets inflamed and swollen, and that's what the doctor can see when they look inside and say you've got an ear infection, is because of all of this fluid and infection that's actually in this area in here. To keep that from happening, okay, there's the auditory ossicles. Okay, to keep that from, I'll come back to those in a second. To keep that from happening, we actually have a little tube right here that allows you to drip fluids down. So any fluids that would normally get trapped here, they come down this little tube called the eustachian tube, and that drips down into your pharynx and down your digestive tract, so it keeps that fluid going. But if that gets blocked or something occurs, then it can't drip down in there, it can't drip away, and it collects, and that causes that ear infection. But once we have, let's go back to the sound waves. Once we have a physical vibration coming from the tympanic membrane, it's going to transmit that vibration to those three little bones, or auditory ossicles: the malleus, the incus, and the stapes. So the malleus is first, the incus is the second bone, and the last one right there is the stapes. Stapes transmits that physical vibration to our inner ear portion called the cochlea. They're called this is all Latin. These are Latin terms, and it's Latin for hammer, for anvil, like a blacksmith used to use, pounding on the anvil, and stirrup, because they're basically kind of shaped that way. So that's where they get it from. You do need to know malleus, incus, stapes, not hammer, anvil, stirrup. Okay. The stapes, which is the last of the ossicles, this one right here, is shaped like a stirrup like this, but it has this little oval plate right here. So this is all little bone here, and it's getting into its information from the other bones, right? So the incus transmits, and then the stapes is this stirrup shape. It's going to transmit that information to an actual opening on the cochlea, which is called the oval window. At that point, we have now moved our physical vibration into the internal ear. So this is the division between middle ear and the internal ear, okay? And moves it towards that next section. Here's my eustachian tube. So remember, this is a cavity right here. It's going to have pressure. It's got air normally filled in there. It's divided from the outside with this tympanic membrane, which means it's a separated cavity, and that can cause a couple issues. First of all, like I said, with fluids, you can get fluids deposited in here. You're going to have to get rid of them, so they will move out the eustachian tube. But on a day-to-day basis, just the difference in the air pressure here and the air pressure out here can put pressure back on that tympanic membrane too. And you know this if you've ever gone up in mountains or down from mountains. You have to pop your mouth, you chew gum or something. You pop, what you're doing is you're opening this tube right here so that air from the mouth and the pharynx can enter, and the pressure here can become equal with the pressure out here. And so we don't have this pressure back here. If you don't do that, you can feel a discomfort, and that discomfort is pressure being put back on that tympanic membrane as you either pull it in. It depends on if you're going up or down in the mountains, but you can either pull it in towards this space as it's trying to fill that space, or you can put pressure out on it, but otherwise, it's not in this normal position, so it becomes pressure. So that's what the eustachian tube does. It really just allows us to have equal pressure here as we do out here, so equalize that pressure. But again, it also, secondarily, another responsibility is to allow any fluids that might accumulate to drip down into the pharynx. So equalize the pressure and allow those fluids. The reason why you have to chew gum or open your mouth and pop that, we used to pop in your ears, is because you have these little valve-like flaps, and you got to get them open to allow for the air to move back and forth. For little kids, and the reason why little kids have more infections than we do, this is an adult ear that you see, and notice the angle of this. So we have an angle. If I come in here, you have this angle right here that's coming in here. For little kids, their skull is a little bit different shaped and it's still developing. That angle isn't nearly as sharp. It's much more of an angle, kind of like this right here. So we have less of a sharp angle. That means the fluids that you would normally drip down here don't have that ability to drip. They're kind of getting stuck back here. So kids are a little more prone to ear infections because of that inability to drip those down. And you end up having to have little tubes inserted. So tubes in the ear is kind of just putting an artificial hole through this to allow the fluids to come out this way instead of dripping down for some kids. Usually they say you outgrow it. It's because your skull is changing shape and your skull is growing, so that angle becomes much more steep right there. All right, moving into the inner ear. So here's my oval window. So this is where that stapes is actually coming in contact. So the stapes, that last auditory ossicle, comes in contact with my inner ear at that point. And now we're going to transmit that physical vibration to this portion here. So we're going to, and it's going to run along through this little snail shell that's right there. Okay. And that's the beginning of the inner ear. The inner ear itself is this complex series of tubes, and it's really a tube within a tube. So I have this outer tube and I have an inner tube inside of that. We call this whole thing of, like this. See how this is going like this? This curls into a snail shell. It's a labyrinth. But basically you have an outer bony portion and you have an inner membranous portion. So that what's in purple right here is a membrane. What's in the light tan color is the bone. So it's a harder, bony outer shell with a smaller tube on the inside that's made up of membranes. And then you have these fluids in between. So I have a fluid between the purple and the outer side, and then inside that purple, and here's a cross section. So there's a fluid right here, and then there's a fluid interior. So there's a fluid inside that purple membranous thing. The movement of the fluids is really important because now this is how we're going to transmit that sound for cochlea, but it's also how you're going to deal with equilibrium and balance. Okay, so fluid, as you move your head, fluid's going to move through these big semicircles. Okay, and as the sound comes in through this oval window, and it's a physical vibration from the bones, it's now going to be transmitted into a vibration of the liquids, and the liquids are going to move as they move through that liquid. The liquids, it's going to move that sound through towards the interior of the snail shell looking thing called the cochlea. All right, so the cochlea is this portion right here. That part is for hearing. Okay. Then you have, there it is. Then you have the three right here, here, and here. Three semicircular canals. So these canals go, so one of them goes at this angle, one of them goes at this angle, right? And then in 3Ds, one of them comes out in a third angle. And I can't do that because it's 3D. But it's basically three different dimensions from each other. And basically that's going to pick up where my head is located as I move in all kinds of directions, and lets me know where my head is so I don't get dizzy and discombobulated. I can figure out, what position my body is in relationship to my head. So these guys are dealing with equilibrium. So two really big functions of the ear here. We have hearing with the cochlea right here, and equilibrium with the semicircular canals. And then in between the two, we have this right here. So I have these canals, and then I have the canals connected to the center portion, and the cochlea connected to the center portion. That's called the vestibule. Okay. And the vestibule is also functioning as part of that. You can see, I sort of wrote over it, but you can see as part of this vestibule that's right here, you can see this swollen, rounded section of the semicircular canals that attach to that. So this is all part of that major section called the vestibule in here, and you can see this portion here. There's the oval window. So that's going to take sound waves and go this way, versus the rest of this is all part of that equilibrium. All right, so the cochlea itself. So now we're talking about hearing, okay? The cochlea itself is going to conduct those sound waves that came in from the external ear to the tympanic membrane that became now a physical vibration, to the bones, transmit that physical vibration to the oval window, which now stimulates these fluid-filled cavities. And we have basically this long tube. So here's if you can look here, right there, that is the cochlea. But if I were to take that and unwind it, it's really just one long tube with a central portion right here. But to save space, we just wind it up. Okay, so it's wound up, but it really is just, if I unwound it, one long tube. And that tube has two different divisions. So it's got this tube on top and this tube on bottom. Sound waves, here's my stapes, right? Here's the oval window. Sound waves come in here, or the vibrations come in here, and stimulate the oval window, and it's going to send vibrations down this long tube. At some point, as these vibrations in this fluid go down this long tube, they're going to have to cross this purple membrane right here. That's the membranous labyrinth. And when they cross, that's what we call pitch. Okay? So that top one is called the scala vestibuli, okay, the upper compartment. It's receiving those vibrations from the oval window and sending them down that way. And again, crossing this membrane at some point for pitch. So high pitch, low pitch. It depends on where it crosses right here. Then as they cross, they're going to come back out this lower vestibule, this lower canal. That's called the scala tympani. And then it's going to leave through another window called the round window, because it has a little more round shape to it. Okay. So scala tympani is the lower compartment. That's where the sound waves have already crossed the membrane and they're coming back out again. So here's the scala vestibuli. At some point, the sound waves from that fluid cross over this membrane, and that's really what's important right here, and into the tympani. And when it crosses the membrane, that's where we're registering sound and we're registering pitch, because this is where the nerves are located. So this is the really important part. What nerves am I stimulating at what point along that long tube that's been curled up? Okay. Here's the round window, the end point. All right. So vestibuli, scala tympani, organ of Corti right here. This is that membrane that's really, really important. The cochlear duct is just part of that membrane of that. And it's where we're going to find that important, really, really important organ of Corti. There's all these membranes in here. You don't really need to know all those membranes, but you do need to know the really important. So, the top membrane is vestibular membrane, the bottom membrane, so top vestibular, because vestibuli. This is base, so it's basilar membrane. And basically housed in here is that organ of Corti. Okay. So this, I'm going to put this link on D2L, but it does show how, as the sound waves come in here, become a physical vibration, with the tympanic membrane, stimulate the first bone, the second bone, and the third bone. So the malleus and stapes right here, stapes, oval window, and then it sends that vibration through that fluid in the scala vestibuli, and then at some point crosses and stimulates nerve cells across these membrane, and eventually will travel back out to the oval window and out again. But this determines pitch. So watch this video because it's a nice video that shows you how pitch is determined in there. Okay, sometimes people are born with, problems that impair different actions in their body, and that, hearing is no different than anything else. And the cochlea is the thing that's going to determine, because it's got the nerve cells, right? So this is the point where you're actually picking up information to send to the brain and stimulating a nerve cell that's going to send that information to the brain. So the cochlea has those nerve cells. If your nerve cells in your cochlea are not getting the information, then you're not going to see, even though everything else might be fine all the way to that point, you're not going to get sound to the brain, or at least the stimulation that says this is sound to the brain, so your brain can interpret it. But a cochlear implant can sort of bypass the cochlea. So it picks up the sound and then transmits an electrical impulse. Remember, everything's just electrical impulse. So once it picks up the sound, it just transmits that electrical impulse directly to the auditory nerve, which is part of that vestibulocochlear nerve. It's one branch of it, vestibulocochlear nerve. Here's the cochlea, right? And it sends that then to the brain for just an electrical impulse to the brain for interpretation. So we just kind of bypass what's going on the middle ear and the internal ear here because or the internal ear, I should say, because the cochlea is not functioning correctly. So just bypass that and send it directly to the nerve and send that impulse to the brain. It's still, they're going to have missed out. Usually you don't get it really early on. So they're going to have missed out on some really early learning that allows us to interpret speech and everything and get that part of the brain to start processing that information. So it's going to take a little bit of speech therapy, some sign language to supplement this, but you can get somebody to that has this particular issue with their hearing to be able to hear again. And you can see in this picture here, so here's the basically receptor, and the kid can control it, the adult can control it, but it picks up on the impulses and makes them an electrical impulse. So you have the headset, you have the microphone, a little ability to change settings on it as they want to. But really it's radio waves that then become electrical signals that is then delivered to cochlea, specifically to the nerve, right? And the nerve then sends that impulse on to the brain, cerebral cortex. And now we have sound. Bypass was not working, get those electrical signals further on. And here is what I was referring to earlier, the organ of Corti. So we have the scala vestibuli on top, the sound's coming in here, and it's got to cross over this, also known as spiral organ, by the way, but organ of Corti. It's got to cross over that. This is where we see actual receptors. So the receptor cells with once again, hair cells. So these very, very fine little hair-looking cells that pick this up. So here's our membranes, right? Basilar membrane up here in the cells. As that sound passes, and depending on where, so I've got this long tube, right, for the cochlea, depending on where it passes through, which part of the membrane, that's going to determine pitch. Those hair cells get stimulated. They send information to the nerve. The nerve then sends it out to the from the cochlear nerve to the auditory nerve, and that becomes that cranial nerve, vestibulocochlear nerves. All right. So this is basically, they're located on, here's the basilar membrane right here. They're located on that basilar membrane. All right. So frequencies of the vibration. So sound waves come in, and basically when it's like through the air, but it works the same through liquids and stuff. But they come in and they're going to be, here's our valleys and our peaks, right? So the distance between these peaks, or you could do the distance between the valleys, it doesn't matter. That distance is called a wave. So the closer they are together, right here to here, the further the less distance between peak to peak, that's going to be a higher pitch. This is going to be a lower pitch. So these waves will travel different distances along that cochlea based off of their peaks and valleys, is what it essentially comes down to. That's the quick version of that. But that's our pitch. So frequencies is frequency is the here to here, That's called a frequency, but that also determines your pitch, low pitch, high pitch. So sound frequencies cause different receptor cells at different points along the cochlea to be stimulated. And then once they're stimulated, they send that information to the nerve. Here's the organ of corti. Here's the little hair cells. So there's pictures of the hair cells. Those are healthy. That's what they should look like, nice and standing up like that. Here are the cells actually in a cross section. So once we get it from the organ of corti and the cochlea, and it's going to be sent along the vestibulocochlear nerve, that's one of your cranial nerves, it's going to go through the, here's the brainstem right here, midbrain pons, and then that gets directed to the auditory cortex eventually so that you can interpret that sound. We can have, besides cochlea being not affected, which is, or not developed properly, which is generally from birth, you can have deafness that occurs due to other things. So later in life, due to damage, due to blockage, whatever. And we can classify this. Conductive damage means that somewhere along this traveling pathway, there's a block. So it could be something physically in the ear canal, like wax, or, kids, they like to stick everything, if there's a hole, they'll stick it up their nose, they'll stick it in their ear, whatever, pebbles and things. So it could be a physical structure that's in there that's going to block that ability of that sound to pass effectively through there. So that would cause conductive hear loss. And this is really the most common. So in some cases, easy. Get rid of the wax, get rid of the obstruction, and you can get the hearing restored again. Sometimes it can be damage that's actually occurred to the tympanic membrane itself. So as we look at the membrane, so somebody's had repeated infections, they've got a tear. That's going to keep that vibration of that membrane. It's going to modify it so you won't have the correct vibration of the membrane, and it can't conduct that information to those auditory ossicles the same way. Could be that they've had so many infections that have damaged that tympanic membrane either through rips and tears. They get scar tissue on it. Again, it's not going to have the right texture, and so it's not going to vibrate accordingly, and it's not going to be able to send that information along. So that would be more of a long-term thing. So if you've got hardening of that tympanic membrane, it can't vibrate like it's supposed to. That can cause loss. If it's a temporary tear, sometimes you get an ear infection and it hurts, and then it tears, and the liquid actually comes out a little bit and it relieves the pain. You can repair it. But repeated tears over a long period of time, or really extreme tears in it, can cause scarring that causes a problem with hearing later on. We can test for hearing loss. There's a couple different tests. Usually it's using some sort of tuning fork. So you have a tuning fork here, just as a quick little test. One of them is called the Weber test. You place it, basically, you hit it on a soft surface and you get it to vibrate. And then you place it on the forehead right here. So if you can hear from both sides, so it sounds like, or both ears are working correctly, it's going to sound like that sound is coming from the front. Okay. But if you've got it in the same place, but you have sound from only one side, that's going to indicate the impaired side. So now I'm not hearing it coming from the front. I'm actually able to pick it up from one side or the other. That indicates that there's some sort of loss on either one of those sides. The Ren test is another one, still tuning fork. So we have the tuning fork, but this time you're placing it behind the ear. So if you reach back behind your ear, there's this little bone right back there, the little that we learned about in lab. So you have that right there, muscle attachment, that kind of stuff. You again hit the tuning fork on a soft surface, not on a table or something, but soft, and then you put it right back there, and you can see the little fork part facing out. The little stem is back there. So when the sound is no longer heard, is what we're looking for here. So once the sound is no longer heard, you move it to the front of the auditory meatus. So bring it around, don't touch, just bring it around in front. Okay. If you have continued sound, that ear has normal hearing. If there's no sound, then there's some sort of hearing loss that's going on in there. Okay. And then we can also have disease due to otosclerosis. Sclerosis means scars. Oto refers to the bone. So new bone is deposited around the stapes. Remember that stapes is meeting up with the oval window right here and has to transmit effectively a physical vibration from that bone to the oval window that then gets carried inside the cochlea in there. If that's ossified, if you've had bone that ossifies and basically seals that bone to the oval window, it can't vibrate, it can't move as much. So you're not going to be able to transmit that sound into the cochlea like you should. Now they can repair that. They can go in and repair that, or they can go in and replace the whole little stapes in there with a wire or plastic replacement. But basically what you have to do is get rid of that little deposited bone for it to vibrate correctly again. Senso means senses. Neural refers to that. So sensorineural deafness is caused by repeated loud sounds. So this is where you want to protect your ears from really loud sounds. So when you're driving down the road and that person has that boom, 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 really, really loud music that they're sharing with you 3 cars away from you, that is going to cause them issues in the future. The airport, Houston Intercontinental is not too far away. The airport, those people that work at the airport out with those planes have to protect their ears. Likewise, jackhammers can do the same thing. Firing ranges, if you go out on a firing range with a gun, the noise over a period of time, it will do damage to all of this information, this portion in here. So what it's doing is it's taking those hair cells, see these nice healthy hair cells, and it's pretty much just breaking them. So see how they've fallen down over here? Once that's done, that's done. You can also have tumors and drugs that work against that too. But the damage comes from those hair cells. So they develop these little bulges, these little blisters. They end up popping, and then they just flop over, and there's tissue degeneration. So you're just not going to be able to pick up the sound as well. As we age, things start to fall apart. So hearing loss is one of those things that we will notice. And a lot of times it's so gradual over such an extended period of time that people really don't notice that they're losing their hearing. But some things can indicate there is a loss. You start having, I'm sorry, I didn't hear you speak up. So soft speech, you lose that ability to hear really, really soft speech. Ringing in the ears, dizziness, because remember equilibrium is tied into this too. But certain sounds to become hard to, the F's, the T's, the S's sound become harder for you to pick up on. You can't hear speech if there's a background noise. So if there's something going on, like the TV's on in the background, and you're unable to really separate that from incoming speech. You've got this, I can't hear you, there's too much background noise, that kind of thing. That indicates that there's a little bit of loss in the hearing. And maybe not too bad at this point. This all goes back to those semicircular canals. But that can help that. And it's just something where, maybe I just need to tune it up a little bit. So you can get a hearing aid that can sort of amplify those sound waves to get more of an electrical signal going to the brain. My mother-in-law had this and denied, because it was so gradual over time. She just was like, I have perfect hearing. I have perfect hearing. And my sister-in-law finally said, let's go prove it. And she had a hearing test done. They were like, you have extensive hearing loss. But you could talk to her with her back to you, and she'd never acknowledge it. I would be driving in her car. She had a little Prius at the time. She's like, my car does not, when you turn on the blinker, it does not make that sound that lets you know the blinker's on. So I just leave my blinker on all the time. I'm like, yes, it does make the sound. You just can't hear the sound. So she ended up with some hearing aids, but she denied that she was having any hearing loss at all until the doctor basically said, it's pretty extensive. But it happens so gradually that sometimes you just don't pay attention to the small symptoms that tell you that it's there. Here's our general summary of what's coming in, sound waves entering and stuff. So this is kind of your steady aid right here. It tells you how this moves through as you're getting that sensation from external to internal, like I walked you through a little while ago. All right, another function of the ear is this portion right here. So the vestibule and these three semicircular canals that go out at three different angles, they're going to determine equilibrium. And we have two types of equilibrium. We have one that's called static. Static equilibrium is like I'm standing still. I know where my head is as I'm being still so that I have some sort of reference point when I start to move or do anything. So this is part of the job of the vestibule right in here. So this is position my head, but everything else is still. Okay. Dynamic means movement. So dynamic equilibrium is when I'm actually moving in some way. It can be very dramatic, like I'm doing with my head right now, or it can be just sort of minor movements like walking or running or whatever else. But this is the job of these three big, I say big, they're still really, really tiny, but relative to the other parts, I guess, semicircular canals. And they go at, like I said, they go at three different angles so that you have this ability, this third one will be pointing out at you, this ability to say, my head is down, my head is up, my head is sideways, but also that I'm turning it or I'm at an angle. So as the fluids move through these, it gives all kinds of signals back to this vestibular nerve. See, there's the cochlear, this is sound right here. And the vestibular is that equilibrium. And then these two nerves actually come together and that becomes that vestibular cochlear nerve. But it does have branches. So the vestibular nerve picks up on all of this movement and then sends that back to the brain for informational. Where am I? What am I doing? How can I make adjustments? So first the vestibule, remember that is your static equilibrium. So while you're standing still. And the vestibule is broken up into different parts. We have the utricle, we have the saccule, and we have the macula. But basically, those are three kind of swollen, separated areas within that vestibule. And they're just really what you need to know is part of that static equilibrium. The macula is going to be, so these are the sections, the utricle and saccule. The macula itself is where the hair cells are going to be located. So we need to, or at least communicate with. So the macula is kind of, you need to pay more attention to that than just realize that the utricle and saccular are sections of the vestibule. So the macula responds to the change in your head position. So I'm sitting still, but I change my head position, like this woman here. It goes down. What's happening is you have these things like little otoliths right here. And when your head like dips down or dips up again, you're going to have movement of these. So these kind of move and shift position. And when they do, they stimulate these little hair cells and they make those shift positions. That stimulates them, they send information down the nerves, and that gives your brain an idea of what my head is doing or where my head is located. So what is my movement going to be at this point? All right, where am I located at this time? Because remember, we're still talking about with vestibule, it's the static. The semicircular canals are more involved in that dynamic equilibrium, so that movement here. So they've got to pick up on movement, and they have to do pretty quickly, because think about it, if you move and you immediately get dizzy, then you would have to take time to recover. So they have to be able to move and figure out my head is now in this position, and how do I respond to that? You have what's called the ampulla. So the ampulla is this thing, and again, it's going to respond to the ampulla is actually, sorry, this space around it. This is the crista ampullaris that's located inside the ampulla. So when I looked at my semicircular canals and I showed you a picture and I said, there's the semicircular canals, and then at one end, they swell out, that's the ampulla. So this is the ampulla. And inside of the ampulla, you have this crista ampullaris, okay? And basically, when movement occurs, this is going to shift position in some way. It bends. And then when it shifts, it bends those little hair cells So once again, the hair cells are the important part here. So those hair cells start to bend, and when they bend, they send information down the nerve. They stimulate the nerve. So here's that crista ampularis. There's the hair cells. So crista ampularis with the hair cells, and that send that information. If you can see here in this picture, you can see how it bends. So as she starts rotating her head and moving her head in movement, it's going to bend this whole cup right here, crista ampularis, and then stimulate those nerve cells on the inside. And that's it for this round. I'll pick you up on the rest of it in a little bit.